Our next presenter is Dr. Trish Steinhilber, and Dr. Steinhilber is the coordinator of the Ag Nutrient Management Program. Today she'll be presenting the presentation titled Beneficial Use of Gypsum in Crop Production and Soil Management.
Hello everybody. I know this is a busy time of the year and I appreciate your tuning in for this last in our winter series of continuing education. I want to bring you up to speed with some of the things going on with gypsum, and I think you'll understand some of the reasons why this topic was included in this year's series once we get going on our talk. We're going to talk about what gypsum is and what's driving the current interest. We're going to talk about how gypsum might improve soil's chemical and physical properties. And in order to do that, I'm going to have to talk to you about some of the techniques and equipment that are actually used for these studies of effectiveness. Now, first of all, I want you to have a clear idea of what gypsum is. It's calcium sulfate dihydrate, which means it has 2 molecules of water associated with every molecule of calcium and sulfate. It is a neutral salt, which means it does not change the pH of the system it dissolves in. It can be synthesized, of course, that is made up from the components, but it's also produced as a byproduct of several industries, and I'm going to emphasize 2 of the industries that produce it as a byproduct in our discussion today. It's a very interesting mineral in the fact that in a number of parts in the world, including several parts of the United States, it's basically found as an evaporite, that is, as salts that accumulate from the evaporation of water. And these are considered sedentary rock formations. Right. Here's an example of one of the formations. This is actually the White Sands National Monument in south central New Mexico. This is sand-sized gypsum that accumulates from being windblown from an ancient lake called Lake Lucero. And there are actually 275 square miles of what's called a gypsum dune field. It's northeast of Las Cruces. And those little dots up there, let me get my pointer here for a minute. These are actually people sledding down a dune on a saucer that typically would be used by kids playing in the snow. Right? So let's talk about byproduct gypsum first. There are several byproduct gypsum products out there. This is one that has been found to be acceptable for use. It's called flue gas desulfurization gypsum, or FGD gypsum. It's actually formed during the removal of sulfur dioxide from the stack gases of coal-fired electric generating plants. So you've got this hot gas coming up, rich in sulfur dioxide, and what's done is a limestone suspension is sprayed at the gases, and basically what we end up with after one further step is a gypsum product. All right? At the current time, it's estimated that there's about 10 million tons a year produced in the United States based on some 2012 data, but there's also some projections that show that this amount could increase by a factor of 2 or 3 over the next 15 to 20 years as some additional Clean Air Act restrictions kick in. Another source of byproduct gypsum is from the building industry, and that's recycled drywall, or what I often call gypsum board. Drywall is basically gypsum that's compacted and has a heavy paper layer on each side. There's a certain amount of that that's left over after construction waste that can be crushed, and that can be used as a gypsum source also. There's also byproduct gypsum produced from the phosphorus fertilizer industry, but this has not been found acceptable for agricultural use. It's produced when acid, often phosphoric acid, is added to rock phosphate, and what we get is a combination of calcium phosphate and calcium sulfate, which is gypsum. The calcium sulfate is used in fertilizer and the gypsum is left behind. Now, EPA looked at this product back in the 80s and found that it would only be acceptable for land application if its residual radioactivity was less than 10 picocuries per gram. And in fact, most of it exceeds that. So there are literally billions of tons of this product stacked along the Gulf Coast states, primarily in the states of Florida and Louisiana. And the largest stack actually covers 340 acres and is 200 feet tall. Now, I mention this even though it can't be used because the desire to find a way to assess whether or not this product could be used in agricultural situations was a primary driver for a whole bunch of research projects, some of which I'm going to talk about today, in the southeastern states. The Florida Phosphorus Research Institute funded research in a number of locations to show the benefit of using it and in hopes of getting approval for it to be land applied. Unfortunately, EPA ruled against it. Now, historically, gypsum has been used in the United States, and there's just a super interesting bit of history here. Ben Franklin, who was quite a man of the world, actually was in France for a period of time after we became an independent country. He was called a commissioner to France. I guess it was like an ambassador. And he became aware of the French folks using gypsum for a number of purposes. First of all, gypsum as a rock formation is a nice soft rock called alabaster, and they used it a lot in sculpture because it's a lot softer than marble. But he also saw that it was being used as an agricultural amendment and as a wall finishing product. And he brought that information back to North America, and actually on his farm, along a hillside in Pennsylvania outside Philadelphia in a clover field, in the shape of these words, land plaster used here, he applied the gypsum. And the anecdote is, I don't know if this is true or not, is that the clover grew markedly better where the gypsum had been put on, and people could actually read that vegetative message as they drove by the hillside along a commonly used road. Now again, I have no way of knowing either whether that was true or not, but it's been cited in a number of places. At the time of the early nation, the only source of gypsum was in Nova Scotia. And even though it was on an ocean port, it was still kind of expensive to import. So it was used to a certain extent, but it was never widely used during the early days of the new country. Now, gypsum has been used in agriculture for a variety of reasons for a long time. We have a long history of using it in the U.S. It's used in tremendous quantities in our semi-arid regions of the United States, where we sometimes have what's called sodic soils. And those are soils where more than 15% of their exchange phase is saturated by sodium. And what happens then is that your clays actually repel one another and you get dispersion. And once the water evaporates, your soil seals over. So in the soil test labs in our semi-arid states, Colorado, New Mexico, Arizona, Nevada, you can actually request a test called a gypsum requirement, and it will tell you how much gypsum you need to apply to counteract the effect of the sodium and to get your soil's infiltration and permeability back in shape. And I'd like to emphasize that the typical amount of gypsum that would be applied in those situations is in the 3 to 5 ton per acre range, not far from what our lime requirements or our lime rates would be here. Gypsum's also been used in peanut production in the southeast, particularly Georgia. There's a great need for available calcium in the vicinity of the forming kernel. So they actually dust their plants during early bloom. The gypsum adheres to the leaves and the blooms, and as those blooms move down into the soil for kernel formation, the gypsum is taken with it. And the rate of application under this situation is usually about a half a ton per acre. This appears to be about as low an application rate as one can get with commercial application equipment and the kind of gypsum that's available. And of course, in many parts of the country where low sulfur soils have been identified, particularly if you're growing a high sulfur demanding crop like a legume. Sulfur is used, gypsum has been used as a sulfur source. And again, that typically is in about the half ton per acre range. So why is there a high interest in gypsum now? Well, in December of 2015, USDA NRCS adopted a standard for gypsum use as a soil amendment. Combine that with the fact that there's a lot of this byproduct gypsum from the flue gas desulfurization that's out there in the marketplace. The current utilization of that product, about half of it, goes into the making of drywall. Much of the rest is actually landfill. The fact is we're running out of landfills, and if there's a use for this in agriculture in a sound agronomic way, there certainly is a desire to have it used. And so in Maryland, the gypsum standard is called Maryland 333, and it has these stated ambitions. They want to improve soil health by improving chemical and physical properties, infiltration, and ameliorating subsoil aluminum toxicity. They also hope to improve surface water quality by reducing soluble PN runoff and drainage water and by reducing the transport of pathogens. So this is a pretty big list of things, and there's a lot of information. So I'm going to focus my talk today on the two things that I think will be of greater relevance under our Maryland conditions. I think there's tremendous relevance in ameliorating subsoil aluminum toxicity, and I think there's a lot of interest in reducing soluble phosphorus in runoff and drainage water. So I'm not going to talk about the other aspects today. That's for another day or another time. All right. So first of all, gypsum. Limestone's calcium carbonate, gypsum's calcium sulfate. All right. The reality, though, at least as quoted by one expert, is that gypsum is 200 times more soluble than gypsum. And that's why it's able to do some things in the soil system where limestone is just ineffective. Its solubility on the scale of minerals and things in the soil is considered moderately soluble. It's not as soluble as urea, for example, but a solubility of 2.5 grams per liter is pretty substantial. Now I want to emphasize that I'm talking about ameliorating subsoil acidity. So let's review our terms here carefully. Amelioration means we reduce the impact of it, and gypsum is something that has been shown to do that. We're not neutralizing the acidity. What that means is that you're reacting with the acidic ions and taking them out of that condition, and that's what lime materials do. All right? We are actually talking about a product that can ameliorate acidity, not neutralize acidity. Now, acidic soils are notoriously bad at limiting root exploration, so ameliorating subsoil acidity has some benefits. The fact is that while there's variability across plant species, many crop plants will not explore a highly acidic subsoil. And that's typically a pH less than 5. The reason why most plant physiologists agree that happens is because there are toxic levels of aluminum and the plant avoids it. The plant roots avoid it. And what this means is that your root zone is thus limited and your crop can only access the water and the nutrients in the topsoil above it. There certainly is a belief that we could improve crop productivity if our crops had better access to a larger soil volume. That is, they could go down and explore the subsoil for the nutrients and the water that are held there. And this becomes more important as an issue in areas where the rainfall is not well distributed during the growing season. In many years, in many places, that's Maryland. And since there's a concern that as climate changes, our rainfall patterns are going to change, I think there's a belief that if we can improve the crop's ability to explore a larger soil volume and to a greater depth, that they'll be better able to extract not only the nutrients but the water that's contained therein. All right, now let's review just a little bit. I know this is a diverse audience, and in some cases you folks haven't thought about this for a while, but let's think about a clay platelet, which is what we have here. This is a this could be kaolinite or montmorillonite or whatever you wish, but it has a whole swarm of cations that are absorbed to its surface to neutralize the charge that originated in the clay. And we won't go into why it's there, but it's there. And then out in the soil solution surrounding that clay, we have a solution that's full of both cations and anions, and they neutralize one another. So the adsorbed cations neutralize the charge in the clay, and the soluble cations neutralize one another. So this is one clay we're looking at here. All right, and in order to neutralize the charge on it, it has adsorbed calcium, magnesium, potassium, aluminum, and hydrogen. And if we introduce gypsum into this system, the gypsum will absorb, will dissolve, and a higher concentration of calcium ion and sulfate ion will be present in that soil solution than was there prior to adding the gypsum. Now that's going to cause a disequilibrium, and it's going to cause all kinds of things to happen. All right. So after things equilibrate again, you're going to have calcium, magnesium, potassium, and hydrogen, but they may not be there to the same extent. For example, you've added a big slug of calcium to the soil solution, and in fact, some of that calcium went on the exchange phase. So the calcium on the exchange phase has been increased from 12 to 16. The magnesium, which was not added in the gypsum, is actually disfavored, and we've gone from 3 to 2 units of magnesium. Likewise, the potassium, none of which was added, and it's disfavored too, drops from 6 to 3. The aluminum has been kicked off entirely, and the hydrogen is about the same, 3 and 3. So now you have still some calcium from the gypsum. You have some magnesium that was kicked off the exchange phase by the calcium you added. You have aluminum that was kicked off the exchange phase, and you have some of the potassium that was on the exchange phase now out in the soil solution. So there's two things I want to point out. Things in the soil solution are subject to leaching if we get a heavy rainfall event or you irrigate. So these things are not in as protected a condition as they were when they existed on the exchange phase. And in addition, there's a new kind of entity in the soil solution that we usually don't talk about in nutrient management training, and that is something called an ion pair. Not all the ions in the soil solution exist as free ions. Some of them associate with other things in the solution, and this is more likely to happen if you're highly charged. Well, aluminum has a +3 charge, and sulfate has a -2 charge. So these tend to associate as something called an ion pair, all right? They're not free floating in the soil solution. They're not acting independently in the soil solution. They're acting as a unit. As a unit, as an ion pair, the aluminum is less toxic to the plant roots, all right? So by adding the gypsum, we increased the calcium on the exchange phase. We kicked off some other things, including the aluminum, and the aluminum is now associating with the sulfate in a less toxic form to the roots as an ion pair. Okay, now here's an example of some data from a study by Yost and his buddies in Ohio State, and they applied gypsum, and they looked at the concentration of calcium, potassium, and magnesium a year later in the soil where it had been incorporated. They incorporated to a depth of about 8 inches, and they took their samples from a depth of 0 to 6. So I'm going to ask a couple questions here. Was the exchangeable calcium increased by the application of gypsum? And my second question is, were any of the other cations affected by the application of gypsum? Okay, thanks. Thanks to you who took the time to write a response. Okay, at the 0 treatment, and that's the area that got no gypsum, 938. At 200 pounds, you raised it over 1,000, 1 ton over 1,200, 10 tons over 1,500. I think it's pretty clear that applying the gypsum definitely increased the exchangeable concentration of calcium. Now, there are ways of isolating what's going on in the soil solution from the exchange and a lab basis. So this is an increase in what was on the exchange sites. All right. Yes, gypsum increases exchangeable calcium. So it increases your pool of reserve calcium. The potassium is more of a mixed bag. Not much of a difference in the potassium, up, down, down a little more, down a little. Not a marked change in the potassium. All right. Magnesium went from 93 parts per million to 87 to 77 to 33. All right. Now let me just point out that there's a lot of belief out there that we probably want to keep our calcium and magnesium ratio at about a 10 to 1. And we were there initially. We're not far off here at the 200 pound per acre rate, but at that 10 ton per acre rate, we really decreased the magnesium on the exchange phase a lot. That means we kicked a lot of it out into the soil solution where it's vulnerable to losses. So that whole thing of when you add a significant source of one cation to the system, you increase its concentration, but you do so at the expense of other things. And in this case, we did it at the expense of magnesium. Now, from they did not see any magnesium deficiency in the crops that were grown on this soil, even at the 10 ton per acre treatment. But I will say that it is something that I think we should be cognizant of. And that's particularly true if the crop that's being grown is a forage, because the magnesium concentration in the forage is very important to avoid a disease, a condition of ruminants called grass tetany. All right. Now I want to talk about some equipment we have never discussed before, and that is a cone penetrometer. Some of you might have handheld penetrometers. They're used to see if you've got a dense soil. They're used for measuring soil hardness or soil heavy soil consistence or high soil bulk density. But this is actually a hydraulically driven cone penetrometer, and this was used in the experiment I'm going to talk about next. The benefit of using a hydraulically driven penetrometer is, number one, you can go very deep. Second of all, you can keep your penetration rate constant, and that's very hard to do as a person, and you can eliminate treatment-to-treatment variability. So this basically is going to hydraulically drive this into the soil. It measures the amount of pressure at the cone, and it's going to give you something called a cone index, okay? And this is used by agricultural engineers to measure the hardness or the compactness of a soil by measuring the force that it takes to penetrate it. And the units in the graph I'm going to show you are in megapascals, because this is a scientific publication, but that's roughly equivalent to approximately 150 or 145 pounds per square inch if you think in those terms. So this is an experiment from University of Georgia. There's a whole series of experiments done down there. This is the one done by the soil physicist, and he looked at physical properties or mechanical impedance. All right. Root growth was corollary to that, and while he mentions root growth, he doesn't show any data on it. He did it on the appling soil, which is a Tiplocapludelt, for those of you that speak that language. It's a sandy loam horizon over a BT clay, and there's a drastic demarcation between the two. And in this particular soil, root growth is limited in the subsoil. Well, there's two reasons. It has a pH of 4.7 and it has high soil strength. All right. So gypsum was used here to see whether or not we could do something to ameliorate the subsoil conditions and decrease the soil strength. So, and again, this is an experiment that was driven by that money from the Florida Phosphorus Research Institute. They wanted data to go to EPA and say, look, this stuff is good for land application. Let's give us permission to use it. So the experiment was initiated in the spring of '81. The gypsum was surface applied and disked into the top 8 inches. At the rate of 15 tons per acre. They grew soybeans the first 2 years, then a crop of corn silage, then alfalfa, and they came back in the spring of '85 and measured the impedance with the cone penetrometer. Now this time difference is important, okay? We did not incorporate the gypsum into the subsoil. We're waiting for it to dissolve and be moved down by natural rainfall, and we can't expect to see its benefits overnight. All right? In this case, they waited 4 years. So here's the cone index measured in millipascals. So each unit, one is equivalent to 145, round up to 150, okay? So in the control soil with no gypsum, topsoil doesn't have much soil strength, but you get down into the subsoil and oh my gosh, does it take a lot of pounds per square inch for roots to penetrate that. So 4 years after the gypsum application, again, even the topsoil was a little bit less resistant to the penetrometer, but there's a marked difference in the resistance of the subsoil. So it was pretty clear that adding the gypsum and growing the crops, and I can't emphasize both, had a very positive influence on ameliorating the strength or the hardness of the subsoil. Now, what he didn't show in his graphs, but what he talked about in the study was that he also had some gypsum-treated fallow plots with no crops. And there was no difference in the cone index between the untreated and the gypsum fallow crops. Radcliffe and the folks that did that publication were very clear about saying that the gypsum amendment increased subsoil root activity, and that in turn reduced the mechanical impedance. It was setting the stage for the roots to explore the subsoil that allowed the decrease in impedance. It was not the gypsum itself. And I find that his study has been misquoted by many people who've used it afterwards, who say, well, the gypsum decreased the soil strength. Well, that's not what Radcliffe said, and it's not what he showed. He showed that the amendment changed the subsoil conditions such that roots could explore, and after that happened, the impedance decreased. Okay, now a corollary study to that, there were a lot of treatments out there. He looked at some of them. The soil chemist group looked at others. Sumner was the soil chemist at the time, and Emily Carter was his PhD student. And they looked at the roots and a whole bunch of chemical properties. I'm going to talk about their root stuff today. If you're interested in the rest, I'd be glad to share the pub with you. Again, same set of experiments initiated in 81. The root sampling was in 85. They looked at somewhat different treatments. They looked at the control, the 5 ton per acre rate, and there was also a lime rate at 9 tons per acre that was incorporated to 1 meter. Now, I don't want to give you the impression that anybody thinks that a farmer is going to incorporate his lime to 1 meter, but what they wanted was a good comparison with amelioration of the acidity due to deep lime incorporation. It was there only for comparative purposes, not because it's a practice they think anyone is going to do. And they actually employed something called the Gillison root washer, which allowed them to very effectively and without anyone losing their sanity, separating the roots from the soil. So in spring of 93, they took deep cores down to about 42 inches, segregated that into sections, washed the soil away, and actually measured the root length, how many meters of root they got per cubic meter of soil. Okay, and this is the data from Carter and Sumner. So we're looking at 6-inch increments, 0 to 6, 6 to 12, blah, 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 down to 42. We're looking at the control where no amendment was added, the gypsum and the lime. All right. And this is alfalfa roots. All right. So you can see that in the controlled soil, the majority of the roots are in fact in that top layer with only limited exploration of the roots even down to 12 and 18 inches and very little, if at all, as you go deeper into the soil profile. Now at the other extreme, you see what the deep liming did. And if you can lime down to 1 meter, and I can't imagine what that would cost in terms of tillage, what kind of equipment you need and how much energy it would take, you not only increased the root length in the topsoil, but you increased it in virtually the entire zone that was explored. The gypsum, quite frankly, is in between, but it does a phenomenal job considering all you did was apply it on the surface until it entered the topsoil. It's a practice that could routinely be done by farmers. Lots more root growth, at 6 to 12, lots more at 12 to 18, lots more at 18 to 24, and you even get some root exploration down to about 36 inches. So it's very clear that when you add that gypsum and give it time to move down in the soil profile, that you can make the deeper soil layers more hospitable to the plant roots, and they will explore it. And it's intermediate in the effect of deep liming, but deep liming is just not a practical option for anyone really outside a research farm. Okay, so now I want to talk a little bit about phosphorus and tying up phosphorus. And this is a diagram that we use a lot in teaching. And what we're going to talk about most is this part over here. We talk about the phosphorus cycle in the sense that we know that soluble phosphate ions can actually react with things like calcium and iron and aluminum and form secondary phosphorus minerals. And it's that kind of a reaction that we're capitalizing on when we add things like alum and iron waste and gypsum to soils or to wastes. We're essentially causing the formation of new secondary minerals, just like those that form in the soil under natural conditions. So what happens is the calcium ion reacts with the phosphate ion and it makes calcium phosphate. And yeah, this is one of the mechanisms in the soil for fixing phosphorus, but it also can be a mechanism on the soil surface or in some other environments where we might put it, as I'll show you at the very end today. So there's a variety of different experimental ways people have studied this. There are some lab incubations I'm going to show you. There's rainfall simulation in runoff boxes. There's rainfall simulation under field conditions, and I'll show you that. I actually have no data from what I'll call real natural rainfall because that's so expensive and cumbersome to do. People don't do it very often. Okay, first of all, let's answer this question. Does gypsum reduce either phosphorus soil test or soluble phosphorus levels? And I'll call that P-Sol in a number of places because I got tired of writing it all out. And this is an experiment that was done by the group at the USDA Watershed Lab with some colleagues at Penn State, and it was published in '98 in the Journal of Environmental Quality. And they looked at a variety of materials that they thought might fix phosphorus. But I'm only going to talk about the gypsum because that's what the conversation's about today. They also looked at a number of soils, some from Pennsylvania, some from Maryland, Delaware, some from Ohio, and even one from Washington. They were searching for soils with a wide array of characteristics so they could see whether soils behave similarly. Okay, they did look at two that we're familiar with, the Mattapique and the Pocomoke, and they basically did a lab incubation experiment. They mixed the various wastes with the various soils, let them sit for 21 days, and looked at what was extractable both by soil test and by water. And the reason they chose 21 days is because there's a previous study they did that showed most of what you're going to see in a year's time manifests itself in 21 days, right? So they took a short route. Now again, there are two soils that are here from Maryland and Delaware. The Pocomoke is the black square. The Mattapique, where's Mattapique? They spelled it wrong, but it's up here as a little X. And you can see that this is water-soluble phosphorus now. And this is at the various rates. They did things metrically, but this is what it's equivalent to if you extrapolate it to tons per acre. And you can see that in every single case, there's a drop-off here in the soluble phosphorus if you add gypsum to it. This is the flue gas desulfurization amendment. Okay, so what we learned from this is that, hey, you can have lots of different soils from different places with a whole array of properties. They had a mollisol, they had an alpasol, an ultasol, an entasol, and a septisol. It didn't make any difference. In every case, adding gypsum at the 2.5 ton per acre rate dropped things down precipitously with some decreases thereafter. Okay, now I'm going to ask you this question and then go back to that graph. Is there an advantage to applying 10 tons of gypsum rather than 5 tons in situations where soluble P is your focus? Okay, so let's go back and look at this, and I'd like several of you to come out of your reverie and answer that question. Okay. Good. Okay, so this 20 grams per kilogram, that's our 10-ton rate. This is our 5-ton rate. Personally, if I was paying to get this stuff hauled, 10 tons would cost more than 5 tons. It certainly indicates that the increase from 5 to 10 is probably not worth it. I'm not sure it's worth going from 2.5 to 5, quite frankly. I think you get most of what you're going to get in the 2-ton rate. All right. This is also in line with some of the rates that are recommended in the Maryland 333 gypsum standard, and it's a rate, the 1, 2, 3 tons per acre is a rate a number of people have found to be good for agronomic advantage without causing undue competition and driving your other nutrient levels in the exchange phase down. Okay? So no, I don't think there's an advantage. Let's see. What am I doing here? Okay. Now, here's what happens to the soil test level. One of the things folks thought might happen when they add gypsum to a soil was that they would see a decline in the phosphorus soil test level. So another thing they looked at in the soils after the 21-day incubation was Mailer 3. And in fact, as you can see here, there just isn't any impact on that, all right? The little bit of difference we see here as well within the differences you would see in the same sample analyzed different times. So, and again, this is a wide array of soils in terms of their maturity, but it's also a wide array of soils in terms of their textural classes and important chemical features. So while gypsum was shown to reduce the soluble P, it was not shown to have an impact on the soil test P. Okay, now we're going to look at some data from runoff boxes. And runoff boxes are a standard size. Some guys got together a couple years back, probably 15, 20 years back, and said, okay, we're all doing these runoff boxes. Let's standardize it so we can compare data from one place to another. So it's a box of a specific depth, specific width, specific length. It has drainage holes in the bottom, and at this bottom end, it actually has a gutter that protects the collection part underneath here from the rainfall that's falling on it and doesn't impact that at all. So this is an example of a runoff box, and these are used for many experiments. We've talked about these before. Okay, this is a rainfall simulator, so you can use this inside or outside. If you use it inside, you put your runoff boxes in here, and you can do a number of them because I think 6 fit in here. I'm not sure how many are normally used. What it is an apparatus that has a nozzle that delivers the water at a specific, highly controlled rate, all right? And you're collecting it down below. Okay, so same group, USDA Watershed Lab with some folks at Penn State. They looked at a variety of materials, including gypsum. They looked at a different combination of soils this time, supposedly 3 soils of agricultural importance in the Northeast, one of which was the Hagerstown soil, and that's the one I'm going to show data for because it's a soil typical of our limestone valleys. And they put the runoff boxes at a 5% slope and applied the water at 2 inches per hour. So this is a pretty heavy rainstorm, the likes of which we get a couple times a year. All right. They also looked at bare soil versus grassed surface. Okay, so this is the soluble P from the bare soil where the gypsum was actually mixed in the top 6 inches, and a grassed soil where it was surface applied because there was grass growing on it. All right. Now, they state in their study that they believe the bare condition represents a tilled soil early in the season before your canopy is closed and protects the soil surface, whereas the grass condition simulates a hay, a pasture, or perhaps a buffer strip. All right? And they looked at 3 different rates of application of gypsum. 0 is our control, 5 tons, and 10 tons. All right? So in terms of soluble P, the gypsum decreased the soluble P from 0.45 milligrams to 0.31 to 0.32. So we're seeing some reduction here in what runs off, but we're not seeing more reduction really between the higher rate and the 5-ton rate. All right? We're also seeing a reduction here in the grassed condition, and I will say that the only difference here is the 10-ton per acre rate. the differences here were not significantly different because there was so much variability across boxes. And I will say that the difference that were observed in the bare soil where the gypsum was mixed were not significant at all. And what I mean by that is even though those numbers are numerically different, there is so much variability in the numbers that go into each of those averages that you could have seen that these numbers by chance alone. Okay, now here's an example of the rainfall simulator outside, and the next experiment I'm going to show you actually was done outside. So there are sidewalls on here because you want your water that's coming out of your orifice up here to not be impacted by any wind. So these side screens are to cut down the diversion of the water due to wind. All right? It also makes the rainfall simulator easy to go airborne on a breezy day. So there are some interesting stories from people who've been part of this research team out in the field. All right, now this was a field scale runoff simulation, and this was done by Norton and his group at USDA ARS in Indiana. And they looked at the Indiana Blount loam. Now, the reason I have to go to Indiana for this data is because no one closer did a field scale rainfall simulator. Okay? They had very high soil test levels, but he doesn't say how high in his study, so I have no idea. And this is in a no-till corn bean rotation. He looked at 4 treatments, and I think from that point of view, this was super. Okay, he had a control where he just looked at how much phosphorus ran off from his residue. He looked at poultry litter, and he looked at gypsum and litter, and he looked at gypsum. So we can see what the gypsum does by itself and what it does in combination. The gypsum was applied at a ton per acre, and he simulated rainfall at 2 inches per hour. Again, this is a severe storm, but we often get those. And this is the data he published. And I'm going to focus on this value here, this mustard color value, which is your soluble reactive phosphorus, or what I'll call P-Sol. So under the no-till situation, he did have 2 milligrams per liter of soluble phosphorus. The gypsum actually decreased that. So again, he didn't publish what his soil test values were, but whatever it was, the gypsum cut it in half. All right? Applying the manure on the surface, as you do in a no-till situation, caused an increase from about 2 milligrams per liter to 12 milligrams per liter of soluble phosphorus. But applying your gypsum with your manure, and this was applied, the gypsum was applied over the manure immediately, okay, before the rainfall simulation. You could cut down from a max of 12 units down to looks like maybe 5.5 milligrams per liter. So it's pretty clear that applying gypsum over manure before that first heavy rainfall event can cause a pretty marked reduction in the soluble P. It's still more than what you get if you'd apply no manure at all, and even the gypsum alone is capable of reducing the soluble P from a high P soil. All right. So here's another one I love. This was done in Auburn. They were part of this pot of money that the Florida Phosphorus Research Institute was throwing around. And they were looking at a pasture situation because a lot of their litter is put on pasture. Their poultry industry is in the Piedmont, and the dominant crop used or grown is Bermuda grass pasture. And this is high productivity Bermuda grass pasture. This is Bermuda grass where if you manage your nitrogen right, you can get 10 tons per acre per year. It's an improved Bermuda grass. They actually applied 6 tons of poultry litter because, again, it's a high nitrogen demanding crop, though they did apply it all at once, and that's not recommended. They looked at 4 gypsum rates, 0, 1, 2, 4 tons of desulfurization gas gypsum, and they simulated rainfall at 4.5 inches of water. The good thing about this is they looked at what happened immediately, but they also looked 5 weeks later and 7 months later. So this is going to answer the question, does the effect of adding the gypsum with the manure last? Okay? And this is the data that they show from this comparison. Again, this is soluble P or P-Sol or soluble reactive phosphorus. It goes from 0 up to 30 parts per million or 30 milligrams per liter. For the runoff simulation immediately after, it dropped from 25 to, looks like about 16 with 1 ton to about 10 milligrams per liter with 2 tons, and it actually went up slightly with 3 tons. So again, this 2 ton is coming up as, hey, you might want to stop there because you've seen all you're going to see. 5 weeks later and 7 weeks later, there was no difference. What the authors say is that, look, whatever's soluble probably gets washed out in the first or maybe the first and second rainfall event, so you're not going to see a marked difference later on in the season. But it emphasizes the importance of getting that gypsum out there right away after you apply your manure, and certainly before your first significant rainfall event if you want to see the impact. All right. Now I want to talk about a couple what I'll call emerging technologies. These are things where there's some research to show their effectiveness, but they've not been formally accepted as BMPs. And I guess what I mean by that is you can't go to your district or to NRCS and get money for them yet. They haven't gone through the process of being fully considered and engineering specs written and all the acceptances that have to be done. But I'm going to show you ditch filters and I'm going to show you curtains. Okay, first of all, Brian again is part of that group up at USDA Watershed Lab, but this work was done in conjunction with University of Maryland College Park people as well as folks at UMES, and it was done at the UMES farm. And what they did was put a ditch filter in one of the main ditches leaving the farm, all right? And they designed it to treat as much water as possible that would have flowed through that ditch, but they knew that in a really heavy rainfall event, some of the water might bypass their filter. So they designed it to measure the water in a couple places, not only the amount, but the sample for phosphorus. They sampled upstream of the filter, downstream of the filter, and they also had a mechanism to collect and measure the bypass water that didn't go through the filter at all. And they looked at two things. They looked at chemical efficacy, so that is, how good does the ditch filter work at reducing soluble phosphorus when the water flows through it. And then they also looked at the system efficiency. That is, how good is the overall filter system at treating the total water, what goes through, and the bypass. That is bypass significant? All right. So here's a diagram based on how they describe it. You've got a field, you've got a ditch. They put drains in the bottom, the same kind of drain you'd put in your septic tank leach field. And then on top of it, they put a mixture of sand and gypsum. Right? Okay, here's what they found. The soluble calcium dissolves from the gypsum. It does react with soluble phosphorus, and it forms calcium phosphates. The annual chemical efficiency varied from 57% to 90%. All right. The per storm chemical efficiency was as low as a -11. That means there was more downstream than upstream, to a high of 99%. Right? The system efficiency was low, but it was low because 93% of the flow passed during exceptionally large storms. All right. The system efficacy varied from 17 to 30%, right? 17 sometimes, 30% other times. They described what they saw as being disappointingly low in treating the ditch drained water, all right? They would have liked it higher in order to go to bat for it, I guess, all right? But they did come up with an idea for another study. The thought is, and there was a study going on at the same time that looked at how much of the water of the ditch came from shallow subsurface flow. So they said, well, okay, instead of treating the water in the ditch, let's find a way to intercept that shallow groundwater flow going into the ditch. And they call this structure, for want of a better term, a gypsum curtain. Now, you can have curtains built of other things, but this is a gypsum curtain. And essentially, it's a trench put in adjacent to the ditch. It intercepts the shallow groundwater before it reaches the ditch, and you fill it in with some material that has been shown to sorb phosphorus, like gypsum. You don't have any bypass flow because you install it in such a way that it intercepts the subsurface flow. And their data suggests that you can get very large reductions in soluble P. Okay, so let's look at this. You've got a field. You put in a gypsum curtain. It's deeper than your ditch, all right? It intercepts everything, well, a lot of what's going into the ditch. I don't want to say everything. All right. You put monitoring wells in here so you can see what it is before the curtain. You put monitoring wells in here so you can see what it is after the curtain. And in fact, in the shallow layer up here, they found a reduction from 5 parts per million soluble P before the curtain to 0.2 parts per million soluble P after the curtain. All right. So it's pretty clear that this can work. I'm not saying it's cheap, but it can work. All right. So let's wrap this up now, some general guidance. Some of the impacts you're going to see are immediate and short term, and that would be applying gypsum over manure to reduce the soluble P. Some impacts might take a couple years, but they're also going to last a longer time. And this would be the application of gypsum to ameliorate subsoil acidity. And I think several of the studies showed that we should observe agronomically sound rates. We don't just want to go out and add whatever, because those high rates did show a pretty significant reduction in exchangeable magnesium, and it was way below the ideal 10-to-1 rate between calcium and magnesium. All right. Some cautions. This flue gas desulfurization gypsum is made by spraying a gypsum suspension on this hot gas that contains sulfur dioxide. In some cases, there's unreacted lime in the flue gas desulfurization gypsum. So one of the things a person should know about their gypsum is, what is its calcium carbonate equivalent? Because if it also has unreacted lime, you need to take that into account when applying it. It is, in my opinion, a good idea to monitor your magnesium soil test levels and to keep your magnesium and calcium in balance. And here's a warning if you decide to apply this stuff on a pasture. You need to keep your ruminants off until the rainfall washes the gypsum off the leaves, because the sulfate can cause sulfate poisoning, or a condition called polioencephalomalacia, or PEM. The sulfate interferes with thiamine metabolism. It actually cleaves the thiamine molecule. So your animals suffer basically thiamine deficiency due to sulfate poisoning. It sounds like a pretty nasty condition. It can lead to paralysis, blindness, and death. So if someone decides to apply it on a pasture, they need to be very careful to keep their ruminants off until after the rain has washed the material off onto the soil. Okay, with that, I'm going to show you another gypsum sand dune deposit, and this is in Guadalupe Mountain National Park in Texas. Again, this has been blown over from an old lake bed, and if you have any questions, let me know.